Welcome to the AI Research Roundup. I'm Alex. Today, we're looking at a paper from the Hugging Face trending list, published on October 9, 2025, about 2 days ago. This paper introduces a feed-forward recurrent Gaussian splatting model that uses rendering error as a feedback signal, achieving plus 3.3 dBPSNR over 3 DGS while being about 100 times faster than per-scene optimization. The paper is titled ReSplat, Learning Recurrent Gaussian Splats, and as we will see later, the results are really impressive. Beyond that highlight, the method cuts the Gaussian count to about 1/16, speeds rendering by roughly 4 times, improves over its own initialization by 2.7 dB, and over depth splat by 2.6 dB, and generalizes across views and resolutions. Alright, the introduction set the stage with speed and quality claims. Figure 1 presents the headline evidence, combining a performance plot with side-by-side renderings. The left plot shows PSNR rising across iterations, with ReSplat improving steadily and overtaking single-pass feed-forward baselines after about 3 updates. The right panels compare renders, where the recurrent refinement sharpens edges and reduces floaters versus MV-splat and depth splat, approaching the ground truth while remaining fast. So, Figure 1 showed the gains from iterative refinement. Figure 2 explains how that refinement works. The left panel depicts initialization. Input images become 1/4 resolution depth maps, which unproject to a point cloud, and KNN plus global attention regress a compact set of Gaussians in a 1/16 subsampled space. The right panel illustrates the recurrent loop that renders views, computes feature-level errors, propagates them with global attention, and predicts parameter deltas with KNN attention, which repeats for several steps. So Figure 2 explained the recurrent loop. Figure 3 shows side-by-side renders on the DL3DV dataset. The columns compare ground truth, 3 DGS optimization, MV-splat, depth splat, and ReSplat. ReSplat produces crisper edges and cleaner textures, which is clearest on signage, ceiling lines, and plant shelves, because the recurrent updates reduce floaters and blur. The backgrounds also look more stable across views, so fine foliage and brick patterns remain detailed while staying faithful to geometry. Alright, the previous figure highlighted visual quality. Table 1 reports 8 view results on DL3DV, showing the recurrent model reaching about 26.8 dBPSNR with 0.85 SSIM after 3 updates, while 3 DGS plateaus near 23.5 dB despite thousands of iterations. The method uses about 246,000 Gaussians, whereas MV-splat and depth splat push roughly 3.9 million, which explains faster rendering. Render time stays near 7/10,000ths of a second per frame, about 4 times quicker than the per pixel baselines. So the previous table focused on 8 views. Table 2 evaluates 16 input views on DL3DV. The table shows ReSplat reaching about 23.2 dBPSNR and 0.755 SSIM after 2 iterations, which surpasses long LRM at roughly 22.7 dB. ReSplat uses about 518,000 Gaussians, roughly 4 times fewer than long LRM, yet quality still improves. Reconstruction time rises with iterations, from about 0.7 to 1.7 seconds, which remains practical given the accuracy gains. Alright, the previous table compared 16 view results. Figure 4 shows how the recurrent refinement generalizes beyond the training setup. The left panel reports cross-dataset gains, where PSNR climbs over iterations and the boost is larger on real estate 10K, which indicates the feedback from rendering error helps shrink the domain gap. The right panel tracks cross-resolution performance, staying strong from 512 by 960 down to 320 by 640, with roughly 4 decibel improvement over iteration 0. Wrapping up, 2 takeaways stand out. Using rendering error as a feedback signal lets a feed-forward model act like an optimizer, so quality climbs in a few steps while staying fast, and a compact Gaussian set delivers speed and generalization across datasets and resolutions. The implications reach 3D content creation, robotics, and mixed reality. That is it for this episode of the AI Research Roundup. I am Alex. Thanks for listening.